Maar ja, ik was echt helemaal... Ja. Hola!
Goedemiddag mensen. Er gaat een presentatie plaatsvinden. Dus vraag uw aandacht.
Okay, let's start the thing then. So, hello, how is everybody? Nice, because today I am going to blow your minds and also your ears. Thanks to my atrocious English accent. Sorry. So, internet from the MSX. It's been an interesting ride that started in the early 2000s. There were some interesting pieces of software and hardware. By 2010, all the infrastructure was more or less done. And we even got some interesting pieces of software like the Twitter client. We will never forget you, Twitter. Also we got Dropbox. And more recently, we got MSX Hub, which is a repository of software directly downloadable from your MSX. And of course the File Hunter browser, a very nice piece of software as well. But unfortunately, an evil force came to make life difficult for us, the MSX users who want to use internet. TLS, Transport Layer Security, also known as SSL, Secure Socket Layers, also known as the HTTPS with that green thing in the side. So this is apparently a big deal for our poor MSX machines. Why? Well, what does imply to implement somehow support for TLS? Well, there is an RFC, which is the official specification of the document. It's not a short one, it's quite long, 160 pages, not bad. But what is this about? Okay, there is an initial exchange of messages between client and server, and the thing is that data is transferred using symmetric encryption, so that it cannot be deciphered by an attacker, and using hashing for authentication to make sure that what you receive is what I sent. And what is the mathematics, the algorithms behind that? Well, there is the symmetric encryption algorithm, which implies a lot of stuff with the data, rotations, additions, logic operations, etc. But you have several modes of operation inside the protocol, which implies even more weird stuff. Yeah, we get that byte, we scramble it, we rotate, a lot of things. And we have also another protocol for hashing based on a message. This implies also the derivation of encryption keys. We also have the specification for the hash itself. So basically the security of the entire protocol is based on how complicated and boring and annoying it is to develop. So could that be implemented on MSX? Okay, so or on in Z80 more generally. AI says maybe it's not a good idea to even try. Human A says I don't think a Z80 machine could do it really. But what if we just try and see what happens? So this was supposed to be a live presentation, but we don't have an MSX here, so it's going to be a video.
And it's TLS version 3?
Sorry?
It's TLS version 3? TLS?
3 what? Sorry?
1.3, the TLS?
Yes, yes. Oh, wow. It worked. Yeah, that seems that whoever did that testing server is not very literate in TLS, and they don't know that it's impossible to do it in 3 MHz SID80. But somehow I did it. That's the thing.
No focus.
Next one. Okay, but there is always a but. This implementation uses a very dirty trick to actually work. Okay, so before actual encrypted communication happens, a key exchange needs to happen. This implies I generate a private key, from this I generate a public key, I send the public key to the server sends me its own public key, and by mixing everything, we get a shared key that has not been transmitted explicitly. And what is that exact operation that needs to be done? Well, it implies exponentiation and modular arithmetic with very big numbers. And by very big numbers, I mean something like those monsters. This is not something that, this time it's true that this is not feasible really on a SET80. So what did I do? Okay, I discovered a very dirty trick. If I choose the number 1, so 00001 as the private key, and send the corresponding public key to the server, then the public key that the server sends me is directly the shared secret. Okay, this defeats the entire purpose of the protocol because there is no security at all, but the idea here was to achieve compatibility, not security. If you use this implementation for accessing your bank details, for example, you are crazy. So don't do it, please. A little bit of how I tackle the development of this. So, such a project has what I very cleverly call two-dimensional complexity. First, the protocol itself is not simple. Second, programming in assembler is not simple either. So if I just start, let's call it byte coding, and start typing code, whenever something fails, I don't know whether I didn't understand the protocol, how it works, or I understood it, but I failed to implement it properly. So how can we separate those two things? Well, first, let's tackle the protocol complexity. I developed a TLS client looking at the protocol in a high-level language. In my case, it was C# because it's the language I am most comfortable with. So yeah, I just read the specification and implemented it. That took me something like 2 weeks. It was not a big thing, but by doing this, I was sure that I understood how the protocol works. After this, I started to get that C# implementation and replace gradually C# bits with SET8 code, for which I needed 2 tools, also made by me, by the way. Nestor80, which is a SET80 assembler in C#, and SID80.NET, which is a SET80 emulator, also in C#. So the procedure was, okay, let's get one piece of code, implement it in SET80 assembler. In this example is the SHA hashing routine. So I create a very small piece of code in C# that loads the registers and assembles the code and loads it in the emulator and executes it. And then I go to the original C# implementation and replace the native computation of the hash with the SET80 hash. I run it. If it still works, great, we have this part solved. Let's go to the following one. And by doing this step by step, that's it. Working implementation of TLS 1.3 for SET80. And It's in GitHub, but I didn't want to spoil the surprise. You can take note of the URL, but for now it's a private repository. And I plan to make it public in the future. In the future is after this talk, so not very far in the future. And that's it. That's the presentation.
Thank you.
I must say also I didn't make a slide for that, but this implementation is not very practical for all the cases. In the video you saw how an R800 took a lot of time to connect to the server. The problem is that a connection needs to be established. The server sends a certificate which is 4 or 5 kilobytes. I need to hash the certificate, send it back like, okay, I got your certificate, right? And that same server that you saw in set 83 MHz mode times out before all of that is possible. So in some cases it's going to work, in other cases it's not going to work depending on how patient the software of the server is. Yeah, so I did it kind of.
Well, but can you cache it? Because you need the private key or so if you make a PC kind of thing that hashes.
The thing is that the key is different for each session.
Yeah.
There is a mechanism called session resumption in which the server sends an intermediate key that you can send back using all the encryption keys. Maybe it could be doable, but for that first version I didn't implement it.
Okay. And another thing, I think in TLS you can downgrade the algorithm and the, so you chose a known algorithm, the one that is the least computing intensive?
I am using already the less powerful algorithm that is allowed by the specification.
The AES
So, yeah.
64?
AES 124 and SHA 256.
Okay.
There are more powerful ones, but
Yeah.
not less. Also, I implemented TLS 1.3 not only because it's the most modern one, because it's also the simplest one. Paradoxically, that algorithm is a simplification compared to TLS 1.2. So yeah, that helped me a bit.
Mm-hmm.
So well, yeah.
Can you briefly click through the previous slides because the previous presentation was a little.
The previous slide, that one. Okay, this is the code that you are going to be able to see in the repository. This is the README on the main file. Just that. Anything else? Yeah.
So I guess I'm a bit new to this, but I've always been thinking with more and more encryption on the net, the way for MSX to get on the net would be to, in the cartridge or whatever extension you have to get on the net, you would do encryption stuff in hardware if possible. Has that been discussed in any communities?
That's actually the practical way to do it.
Yeah.
But I wanted, just for the fun, I wanted to do it purely in software.
Obviously, yeah, I love the challenge.
But yeah, for practical purposes, it should be done in hardware, and there are some things already. For example, there is a Wi-Fi cartridge that already handles that, done by Charlie Rompe. But if we had a mathematical module that could handle the encryption itself, or at very least the key derivation, that would already be helpful, because aside for the encryption and the keys, the TLS protocol itself is not that complicated. It's all the mathematics what makes it complex.
Yes,
Really.
it is.
So it means that you don't need a new version of UNAPI?
Sorry?
You don't need a new version of UNAPI if you have a hardware-based solution for the key derivation?
No, actually, I added support for TLS in UNAPI in the last version, in case somehow it's implemented. The example application that you have seen, which is just a very simple telnet client, I implemented TLS in the telnet client itself.
Okay.
So now the next step could be to add all of this to Internestor itself.
Yeah.
But that's something that maybe I will do it later. But another option is to integrate the code itself in the application program. I have tried to document it exhaustively so it can be done more or less easily. Also not only on MSX but on other platforms as well. The UNAPI module is completely separate from the rest, so it can be easily replaced.
Mm-hmm. So SimOS can also use that.
Exactly. If they implement the data transport module with the same routing signatures.
What kind of how did you like the performance?
The performance. Well, it works and I am happy with that. So the performance is more or less acceptable after the initial hard part, which is the negotiation. And if you are not able to connect to a server with this, it's because it timeouts on the negotiation phase, which is a pity because the server is sending me a certificate that I am going to ignore, but the protocol dictates that it needs to send it to me. I need to parse it and hash it to send it back to prove that I have received it uncompromised, and then after that the keys are generated and the data exchange can start. And
The master connection is up the encryption is symmetric.
yeah, the symmetric encryption is not that resource intensive. Of course, it's not immediate, but it's manageable. You are going to notice a delay, but not a dramatic delay, like at the beginning of the video when it takes like 15 seconds just to exchange the certificates.
Maybe you can show the trick you use, because I don't think he...
The trick. What was it? Okay, so that's it. So I use the number 1 as my own private key. I send it to the server. The server is, I don't know the exact details, but it's somehow multiplying that 1 by its own public key. So its own public key is the final shared secret. Of course, if someone intercepts this is not secure at all, but it's the only way of doing it purely by software. So, any more questions? We have like 10 minutes. I thought I had the aspect of that, but another advantage of using that set80 code running in a C# project is that I can unit test set8 code with C# code, which is really nice and very, very useful. 3, 2, 1, solved. Thank you very much.